So we saw how to calculate the motional EMF in a variety of motion. We started with the translatory motion, then we moved to the pure rotational motion, and then we saw combined motion, which can be eventually converted into the pure rotational motion, and then we can find the answer. Okay. So today I'm going to take the emotional for SHM. So let's think about the simple harmonic motion. Imagine we have a scenario in which we have transverse magnetic field, and using some external agent we are setting a rod into oscillatory motion. Okay. So this thin rod is performing oscillatory motion, to and fro motion. The length is L, and if I choose this as origin, so the x coordinate of the rod at any instant is given by a sine omega t. Now the formula of the induced EMF remains the same. It is BVL, or you can say BLV. So BLV we can write as BL, and V we can replace by dx by dt. So the E emotional becomes BL A omega cos omega t. And because it's a sinusoidal value, so this is the maximum value. So this is the, I can say E equals to E naught cos omega t, where E naught is so this is the maximum EMF induced in the process. So you may be asked a question like this. The other question may be like this. Imagine if you have a conducting rod, I mean not rod, a wire. I'll choose a conducting wire. Attached to an insulating mass, and this is set into a small oscillation, because only for a small oscillation it will perform SHM. For large oscillation, we know it will perform oscillatory motion but not SHM. Why? Because SHM is a mathematical scenario in which the acceleration and the displacements are proportional. So let's say you release a bob from theta naught, release from rest at t equals to 0, which means this bob will oscillate to and fro with angular displacement amplitude, or simply angular amplitude, you can say theta naught. Okay. So it will oscillate between these two extremes. So at any instant, let's say you are at this particular location, And the angle which you make with the vertical, that's called theta. Then the angular position at any instant, the instantaneous angular position. Theta we can write as theta naught cos omega naught t. We write omega naught t for some interesting reason. So here the omega naught will come to know later on is equals to the G by L for SHM. So the instantaneous angular position we can write as the initial value. And why we are taking cos? Because we know cos 0 is 1. So the answer will match the condition that we described. And this is the equation of SHM for angular displacement, similar to what we did previously. Now, as it is set into a session, it will move to and fro with some angular velocity, right? So what is the angular velocity value? See, we need to understand this is not the velocity, this is called angular frequency. Now we are talking about angular velocity, which is defined as the rate at which you change the angle, g theta dt, right?
Yes, sir.
And if you differentiate the above equation, what will you get? You can differentiate this one, which is easy to write.
Theta naught sine omega. Sorry, theta naught omega naught sine omega t minus.
Minus. Very well. So this is the question of rotational motion, isn't it? We have done this.
Yes.
So if I set up this entire thing in a transverse magnetic field, then the induced EMF we can directly write as half b omega L square. Let's say L is the length of pendulum. So the wire, this, because this is the conducting wire, so this will also have the induced EMF, and we can get the answer. So you can clearly see that we can correlate any uh, mathematically, related motion, and we can convert it into a question of, a question of induced EMF. So this has been a common practice, and okay, we'll just add the value. I mean, don't write the sign. Sign we can decide on our own. So this turns out to be b theta naught omega naught L square by 2 into sine omega naught into t. Just Okay, so I hope you understood this. The E max we can write it. Again, we can write in a similar fashion, and the maximum EMF induced will be. So it's a very simple. I mean, if you look at any question of motional EMF, if you understand the motion idea or concept of motion, then any motion can be either thought as translatory or oscillatory or rotatory. So all of the question will have almost similar way to analyze the uh, EMF, motional EMF. Okay,
Yes,
I
sir.
hope this is clear.
Yes, sir. Sir, are we taking into account the gravity in here?
Yeah, because of gravity only it is performing a system. Because
Yes,
magnetic field will do nothing. No force will be applied by magnetic field.
sir.
Force
Yes, sir.
is only applied when there is a current through the conductor, right? ILB.
Yes, sir.
But if there is no current, then it is the gravity which is performing the system. So gravity is indeed present. Otherwise, I couldn't have used the G value here, right?
Yes, sir.
The the last variety which is coming to my mind as of now. I mean, of course, there are many, and it is like. But this party I haven't taught you, so that's why you may find it a bit difficult. But let me explain. Imagine we have a string which is fixed between the two ends, and the length is L. And now what we are doing is we are trying to set this string into oscillation. So let's say we have something called tuning fork. This is just symbolic, it is not the way it is. And now this string is set into vibration. So now the property is that when we set something into vibration using a tuning fork, again I'm saying this is just a symbolic, it is not connected actually. So in a reality, when I'm saying a tuning fork, it will be connected with the rope, and it is the tuning fork which will set the string into oscillation. And
Yes.
because the agent, the source which sets the system into oscillation is the tuning fork, so in case of you can say a resonating condition, the string will start vibrating with the same frequency as that of the tuning fork. That's the whole rule. So the symbolic meaning is that eventually the string will be set into oscillation with the frequency equivalent of the frequency of the tuning fork. Okay. So the string will set itself into oscillation with frequency equal to tuning fork. Okay. So string will set itself into oscillation with a frequency equal to tuning fork. Understood?
Yes, sir.
So what happens is that we have something called stationary wave. So when you set one end into oscillation, the wall will reflect back the energy. So in one direction, it is the tuning fork which is supplying the energy. And of course, the tuning fork is oscillated by some agent, maybe a motor driven tuning fork, then it is the electrical energy which is giving the mechanical motion. Or it may be a manually driven tuning fork in which the person who is driving it is giving the required energy. So we do have the source of energy, because at the end of the day, when you set a medium into oscillation, you actually impart energy to the medium. So in any case, energy is coming from some source. So tuning fork is a symbolic to energy source as well. And who is driving the tuning fork is not our concern. What we understand or what we believe, that okay, we are getting some energy, and the energy will propagate through the string. The wall will help in reflecting it. So when the incoming and the reflected will meet each other, a sustained oscillation will happen eventually, and that sustained oscillation, we call it standing wave or stationary wave. And in the simplest mode of vibration, called the fundamental mode of vibration, the string will go up. It will go up slowly, it will come to eventually rest, and it will also go down after crossing the mean position. Okay. So the string will go up and down, and because the string will go up and down, this is how we are setting this into oscillation. And this point we call node. Node means the point which is at permanent rest, and it is like half of oscillation. So if you draw a picture of a oscillation, this is what I'm drawing here.
Yes, sir.
You can clearly see what I'm drawing is the half of the lambda in this case, right? So this is representing how much? So in terms of wavelength, this is lambda by 2. So this is called the fundamental mode of vibration. And in the fundamental mode of vibration, the wavelength is lambda by 2. So we can say lambda by 2 is equal to the length of the oscillating string. So lambda is twice of the length of the oscillating string. I mean, I'm not concerned about the entire length of the string. We are only concerned about what part of the string is into oscillation. And this is precisely what we study. I mean, when we study the musical instrument. So when we have a guitar, and if you press the string of a guitar, and when you pluck the string, you know that from the point at which you have pressed the string till the bottom, only that part is into oscillation, right? So the upper part we exclude from the oscillatory motion, isn't it?
Yes, sir.
So basically, the method of pressing the string is method of varying the length of the string. So in a way, we change the L value because it is directly connected to the lambda, and therefore to generate a frequency of desirable value, we do this modification, and it requires a lot of muscle memory to remember the location and all. And eventually, with extreme practice, people do it so effortlessly that it looks like it's very natural, but somewhere deep down their mind, they keep on counting something. Okay. And then it becomes the reflex after long use. Okay. So that's the professionals.
Okay.
Okay. So do you know how to play guitar?
Sir, no, sir. But I want to learn it.
Any musical instrument?
Sir, I played bongos for a short while at school.
Yeah, it's cool. Bongos was played by the Richard Feynman, the Nobel laureate of physics. So he used to play bongos. But that's good. One should play some sort of musical instrument. It gives a brain rhythm to connect back to mathematical nature of nature, you can say. And it's also good. I mean, as a hobby, it will act as a stress buster at times. We all should
Yes.
have at least one skill in music also. It is required. Okay. So I really wish that I wanted to always learn guitar, but I bought 2 times guitar, but never ever able to get the time to play. So for me, the time was the biggest constraint. I cannot play. Till now, I'm still thinking when I will start. Someday I'll start for sure. Maybe at the age of 50, I'll start playing guitar. Nevertheless. So what we are trying to understand here that when you set this into oscillation, so this will have a well-defined uh, equation of motion. So this is the well-defined equation of motion. And the way we write the equation of motion is very simple. You can think of any particle. So don't think of string at a distance x, imagine a particle. So this particle will go up and down, right? Technically, it will go as much up as much down. So this is performing basically every particle is individually performing SHM. Understood? So
Yes, sir.
for this particle, if I write the equation of SHM for the particle at x, the equation will be some amplitude, and you can see the amplitude will be some function of x, because as you move towards the right, the particle next to it will have bigger amplitude, right?
Yes.
So the amplitude of particle is not same. It varies from particle to particle. So we say that the amplitude will vary with position x. So we write a is a function of x because we don't see it to be constant. In fact, this particle will have zero amplitude, and that is why we call node. So a node is a point at which the particle oscillate with zero amplitude. It means it doesn't oscillate at all. That's the way of saying. So y is equals to some amplitude which we don't know how much. That's called ax. And because it is performing the system, it must be sine or cos. I will just choose sine omega t. Okay. So this is the formula. But further, if we can realize, or you will come to know that the ax itself is a function of some amplitude we write as 2a, and I'll tell you why I write 2a, and then it may become either sine kx or cos kx. Let me choose one of the sine kx. And what is 2a? What is a representing here? A is the amplitude of wave getting superimposed. So basically, this formula y is product of the sum of the two y. The one y which the wave going towards the right will create, and the other y is due to the wave which is coming after reflection, and the two will create the net oscillation. So every particle's oscillation will be decided by not one person or one agent, but by two agents. It's called the virtual agent. So one agent which is the direct agent, the agent which is trying to affect directly the tuning fork. Other is invisible, meaning the other is coming through reflection. So it is like you throw some energy reflect back. So coming in energy is the hypothetically or virtually coming from another source. You can think like this energy is coming from some distinct source. So the agents which are responsible for the overall motion of a particle in a medium is, we say two, there are two agents. One, the incoming, other is the not incoming. One is the direct, other is the reflected one. Do you realize what I'm saying? And
Not exactly.
okay, not exactly, because yeah, you haven't studied this part. Okay, I'll suggest that okay, you should watch my wave and sound chapter. It's really interesting. It's easy also, and then someday I'll cover it in a quick succession. So basically, every wave we call traveling wave, and the way of writing a traveling wave on a string is a sine omega t minus kx. We write like this: a traveling wave question. The another will have a sine omega t plus kx because it is coming back, so it's going this way. This is coming this way. So this equation is basically sum of the two. When you add these two using the pardon.
So is it like, because I mean, like at the starting of this page, you had told the wave first traverses to the other end and gets reflected, and collision happens. Because of that, second wave is
see, energy don't collide. In a way, it's very interesting that there is no collision happening. Rather, there is a effect happening. So what they happen? What happens is like both will try to drive the particle in a fashion which they want. Fashion means, I mean, either I will hit the particle up or down, right?
Yes, sir.
So imagine the wave going towards right is trying to push you up with a greater force. The one coming left from left is trying to push you down with a lesser force. So the net effect will be upward, right? So you will go up. And a similar fashion, if I so imagine if the wave is coming in such a way that it's so powerful that the incoming wave is bigger in powerful and it is trying to push you down, and like the reflected one, and the direct one is trying to pull you up. So one is trying to pull you down, other is trying to pull you up, and the down is dominating, then the up, then the particle will eventually go down. Okay. So
the effect is sort of superposed.
Exactly. The effect is superposed. That is what we call superposition theorem. I mean, superposition is an idea which is prevalent in every aspect of physics. I mean, not only physics, everywhere. So superposition is a property of any linear system. Linear means a system whose behavior can be either decomposed into individual, or we can create a singleton behavior using a large number of behavior getting combined together.
Yes.
So if you look at one event, you can either decompose that event into infinite small events, which are linearly compatible with each other. Or if we know the individual event, then we can predict the overall event. Okay, so their combination or combined behavior can be studied because they are linearly compatible with each other. That is the whole idea of the linear system. Okay. The entire science, the entire physics, we divide into two terms. One is called the linear system, and other is called the non-linear system. In the non-linear system, this superposition doesn't, act the way we know. So there might be some other way for the superposition to work, but it is not in the scope of the JEE or even up to graduation level. Only for masters and above we come to know about the non-linear behavior. Okay. And only for those who are doing real research. Most of the graduates or the master's student are know less physics than a class 12 pass student of who prepare for JEE. Yeah, so those who do masters, they're not genius or intelligent. They're just passing the course somehow. So they're not knowing a lot physics. Of course, they know a lot complex formula because they have mugged up in most of the scenario. So the whole idea is there is something called standing wave. And for a particle at a location x, you can assume if the height is y, what you need to just assume right as of now is, let's say the y we can write as capital A sine omega t sine kx cos kx or whatever. I mean, just use any formula.
Okay, sir.
And the A is the twice of the A of individual. Okay.
Yes.
So if Y we got the answer, so let's say, okay, at the end of the day, you're not bothered about this all formula. What you need to understand is how the EMF is developed is it is based on the motion, isn't it?
Yes, sir.
So technically, if we have, if I choose a small part of the string of dx length, and if we hypothetically, okay, I'll do it on the next page because this is just theory part. So so let's say if I put this entire arrangement into transverse magnetic field. See, again, I'm saying the same thing. All these things that we are learning, we need to understand what is the crux, what we are trying to achieve. We are trying to achieve the motional EMF, right? And let's see if I draw some wave which is something like this. I mean, a lot more symmetry. So the equation of motion, let's say given by some formula A sine omega t sine kx, and this is called the multivariable function. So we have time and position both as a variable. So to find the velocity of a random particle which is located at a random position x, the velocity of the particle, when I say velocity of the particle, it means you can imagine a segment of a tiniest possible segment of this string. So every dx length which you cut in a string will behave as a particle. And we're talking about the v of that particle. So we can say vp equals to velocity of the particle, and this we can write as del y by del t. Why the del symbol has been used? For the obvious reason, it's a multivariable function, so the exact differential is not the right way to write. We are trying to understand the variation of y with time only, because we are talking about one particle. So one particle will have one x, right?
Yes.
So this term is like a constant because it's a finite x will not change. And then we are trying to find the velocity of this particle. So what we need to know is how the y is changing as per time, right? That's the logical thing. So Vp turns out to be how much? The Vp turns out to be a omega cos omega t
Sir,
sine.
what does I mean K signify?
Okay, k is the way of writing 2 pi by lambda.
Oh,
It's called the angular wave number.
okay.
Okay. So the question is, if you look at the particle, if something is going up, something is going down, you can see this entire loop is, the first loop is, let's say, if going up, the next will go down, the next will go up. So there is always the two adjacent loops, what we call loop here, two adjacent loop will be always moving in the opposite direction. So we call them out of phase. But that's okay. If you don't understand the out of phase and all, that's totally okay. So we say that okay, they will move opposite direction. Okay. So now uh, the okay, that's fine. So we are done. So if I choose a small part dx length, and if the velocity is vp, the induced EMF will be how much? Or the most EMF? V, right?
Yes.
We could call it d because it's a elementary value. So d we got this value, and vp we got as a omega cos omega t sine k x and dx. And what we are bothered about is the net EMF for the entire uh, string. It is b a omega, and we take cos omega t outside. Why? Because we want to know the answer at one instant. So at one instant there is one velocity for every particle, so we need to just indicate the sine kx dx.
Yes.
And then the x will vary from, let's say, 0 to L. So this integration is very simple to calculate. The reason is, what we are doing is we are calculating something from 0 to L, but in every loop, if we have odd number of loop, then the equal values will cancel out. We will left with only one, right?
Yes.
And if I know that we have even loop, then all will cancel out because the net EMF will be 0 for the entire system, right?
Yes.
So for even loop, we have, I mean, 0 answer. For odd, we have non-zero answer. So what I'll do is I'll calculate for the one loop. So EMF induced per loop, EMF induced per loop. What we can write per loop? The E equals to B A omega cos omega t integration of 0 to lambda by 2 sine kx dx. What is integration of sine?
So
So
minus cos.
minus cos kx by k, right?
Yes.
So I can change the limit. It is lambda by 2 to 0.
Yes.
So we can write as upper limit, which is cos 0, which is 1 minus, and the lower limit is how much? Cos k lambda by 2.
K lambda. Yes.
Now you can see k lambda by 2 is basically pi.
Yes.
So this is basically 1 minus cos pi, and cos pi is minus 1, which is why this is 2 by. So that's very interesting answer. And so finally, I can add b is actually equals to 2 by k ba omega cos omega t. So this term is called the maximum possible value. So e equals to e naught cos omega t, and therefore the e becomes e naught is how much? 2 ba omega by k. 2 ba 2 ba omega by. So where a is the amplitude of standing wave. So if I express a as twice of a, the smaller wave which made this a, this is 4 ab omega by. So yeah, if you want to write in terms of lambda, uh, so this answer will have, and because this answer we derived since we derived for fundamental mode. What I mean to say fundamental mode, single loop, one loop scenario. So we can write lambda by 2 equals to L. So lambda we can write as 2L. And because k is 2 pi by lambda, so it is pi by L. So therefore, E naught equals to 4a b, and omega is determined by the frequency of tuning fork, and we know frequency right as 2 pi f, and k we got pi by L. So this pi gets cancelled. So E naught turns out to be 8ab f L. Yeah, everything is there, right? 8ab f. So really nice answer at the end of this calculation.
Yes.
So this completes the motional EMF calculation. We are done with the second part of this chapter. So we can now enter the third part. So motional EMF is the essential calculation that without which we can, or we cannot actually solve any of the question. In a way we can solve, but that will be cumbersome. Okay.
Yes.
All right.
Okay.
So let's move to the next concept.
So can you just come back in a minute?
Yeah, sure.
sir.
Yeah.
Yes.
Now this is the EMF maximum EMF induced per loop. So if we have, but we also need to understand that every subsequent loop will have the altering sign convention, right? So
Yes, sir.
if I do something like this, so all will have altering plus minus plus minus.
Yes, sir.
So if one loop will create the plus, other will create minus. So at the end of the day, answer is going to be either this or zero. So the
Yes, sir.
maximum you can get is either zero when number of loop is even, or it is this value when number of loops. So we are not going to get any other answer, right? Understood.
Yes, sir.
And we need to understand this A is for the individual amplitude. Sometimes they mention only capital A. So in terms of capital A, which is the amplitude, see what is the capital A, you can realize here. This is capital A. Here, yeah. So when they give you the equation like this, and then A is you are using A here, then not here. Then E max we can write is so it is either write 8A B F L or A is capital A by 2. It's like 4A B F L. So you have to be careful that which kind of A you are using. The A of the individual or A of the overall value. So when you study the chapter of the wave and sound, you will come to know this more clearly.
Okay, sir.
It's not difficult, just you need to study once. You have to start from a system. So start reading a system that I'll suggest.
Okay, sir.
Now, since we have mastered a variety of EMF calculating technique, so now whatever circuit we come across, if you come across a circuit and if the circuit will have a moving part, so you will only focus on the moving part as of now. And the rule is we are going to replace the moving part equivalent to the EMF battery, EMF a cell with the EMF equivalent of what we would have got using the motional or Faraday's law. And once you replace it, then your job is to solve the way you solve a general circuit. Okay. So now we are going
Yes.
to move towards something called. Okay. So we write pi circuit. So pi is a okay. I have discussed what is pi. So you know the pi symbol. You can also write pi as something like this, and then you can put into any orientation. So this all are pi. So the essence of pi circuit or the idea of pi circuit is not the shape. It is three-sided. A circuit with three sides as a fixed and one side as a open. So that's the whole
Yes.
idea of pi circuit. So if I draw a pi circuit, so we will start with the R circuit in our syllabus. R circuit. So what we have is a resistor R, and after this we have only three parties fixed. The next thing is what we have is called the a slider. So a slider is something which can slide. That's obvious. So at t equals to 0, the slider is given a velocity v naught. So now this is the question of motional EMF, because a moving part is there in a uniform and transverse magnetic field. So this rod is going to be equivalent of a cell or battery, right?
Yes.
So assuming that the rod is having no internal resistance, we can assuming internal resistance of circuit, let's say, or internal resistance of rod, moving rod. So every moving rod with velocity v, that's called v, we can replace by, and if it is a cross field, so v cross b will be upward.
Yes.
So this is a cell of EMF VBL. So that is always there. So when we have a moving part, it will have the induced EMF in that part. And we know that this cell is only for the slider. But because of the slider nature, it completes a loop. So we can clearly see there's a loop here, right?
Yes.
And because of the closed circuit, the current is going to be established. Okay.
Yes.
So this we can convert into a circuit as simple as this. And the moment you convert into circuit like this, the journey from the EMI chapter is over. So now you cannot say that we are learning EMI chapter. Now we are learning the current and electricity, the circuit chapter. So that is the role. Actually, from EMI chapter, we only extract one piece of information, and that is the EMF induced part. But after that, this chapter is actually of no use. So now we have to dump this chapter and we have to think about this new acquired circuit and how to deal with. So because of this circuit, we can think of current I.
Yes.
So the first step is E induced. Now we'll come to this induced part in a while. But look at this scenario. If you look at the current, the slider current is upward, isn't it? So the moment it will move towards the right, the current will move like this. The induced current. Yes or no?
Yes.
And now if I apply because slider is a moving object, so we have to think about the laws of motion. So if I apply the magnetic force on a current carrying a wire, we have, and I mean, we have examined and deduced the answer. It is ILP, IL cross B, right? So L is upward, B is inward. So L cross B is left, right?
Yes.
Which means the rod cannot move with constant velocity. It will slow down. And in
Yes.
fact, it has to slow down. The reason is, until it will not slow down, it will not lose energy. And until it will not lose energy, the circuit will not gain the electrical energy. Because energy is conserved. No?
Yes.
So to drive a circuit, we need energy. And the role of the rod is to drive the circuit. But that phenomena will exist till we have some energy left in the rod. So it is natural for the rod to slow down because the energy that is taken from the rod is actually consumed by the resistor of the circuit in the heat dissipation process. And because of the force analysis, you can also see that the force will act left. So the rod is going to slow down, isn't it?
Yes.
So how we start analyzing problem like this? So the first step of analysis is simple. You choose a random instant. Why random? Because we have discussed that the rod will slow down. So the
Yes.
velocity of the rod is not a constant quantity, rather it's a variable quantity. So velocity is a variable entity, and therefore at any instant we write v and we call this is t. So the first step is we not take the initial condition, we take the general condition and we write something like this. At a general condition, we write the induced EMF. So induced EMF we write only at t equals to t. We don't write t0. Okay. So the answer becomes
Yes.
BLV. BLV. That's so first part is done. L is the gauge length. If you remember, L is the gauge length.
Yes, sir. The one
Done.
enclosed within the rings.
Yeah. Because the one which will be part of the current circuit, okay, the current loop.
Yes.
And now you can write here answer BLV. We are done. So we got the circuit part. The next step is what is I induce. That's pretty simple because it's a simple circuit, R circuit. So I induce is E induce upon resistance.
Yes, sir.
No big deal. And
Yes.
mind you, V is a variable. So current will persist in the circuit as long as the rod is in motion. The moment rod will come to rest, the current will cease to exist. Okay. So this
Yes.
part is also very logical. But the next part is if you talk about the circuit, we have discussed the current and then it's over. I mean, current will depend on speed. So our goal is can we determine the velocity as a function of time t? So to say that okay, we want to know the velocity as a function of time t, I need to know how v is changing. And when I say we need to know how v is changing is as good as saying what is the acceleration. Can you tell me the acceleration? But to tell the acceleration, I need to know the ABD, the free body diagram, right?
Yes, sir.
So the next logical step is draw the ABD for the moving part, right? Of course, we are not going to write for circuit. So for slider, it is imperative to draw the ABD. And if you draw the ABD, we have realized that the only force acting is ILB and it is going towards right. And because the force is against the motion, so it will create the retardation and therefore the acceleration will be equals to minus of retardation. And what is the value of retardation? What we can write here? A by M,
Yes,
where
sir.
M is the mass of the rod, and therefore it will become ILB by M, and we know what is I.
Yes, sir.
So the A becomes minus B square L square by small mr into V. And that's why I said I need to know how V is changing. To tell you the value of V at a given instant, you need to tell me first how V is changing. Then only I can tell you, and how V is changing is equivalent of saying what is the acceleration. Okay, these are all like some symbolic meaning. I mean, if you say, if you understand one thing, you can convert it into some more refined way of saying it. So by definition, how V is changing is expressed in terms of acceleration, and we got the acceleration. Once you get the acceleration, the job of laws of motion chapter is over. Now, laws
Yes,
of
sir.
motion is only when you get the acceleration. That's the whole idea of solving the laws of motion. Once you are good with the laws of motion, the next step is very simple. It's very simple. Can you find V as a function of time t? Because A we are
Yes, sir.
getting as a function of V, so next is kinematic equation. Generally, before you proceed further, what I will suggest, write as minus kV, and this entire term will become K.
Yes.
Okay. So the next step, again, see, we are moving in a very logical sequence, and we're trying to question ourselves, and we're getting the very nice, appropriate answer also, where A is B square L square by. Understood?
Yes. Sir,
Yeah. So now your job is to proceed from here and tell me the velocity when as a function of time t, and also find the velocity as a function of displacement x.
sir, as a function of time t, I'm getting p is equal to v naught by 1 plus kt.
Not possible.
Sir, v is equal to u plus at.
No, you can't use v equals to plus 80. It's a variable acceleration. That is only meant for the constant acceleration, right?
Oh, yes, sir.
What a big mistake, huh? Mm.
So,
Yeah.
sir, k ln of v naught by v is equal to t.
Yeah. So what is v not v equals to then? Can you rearrange to get v?
Yes. Sir, v naught into e power minus t by k.
So v equals to v naught e power minus kt, right? Like this?
Sir, t by k.
No, then it's again some mistake.
Yes, sir. It's kt.
So v we can write as dv by dt, na?
Yes, sir.
So the v equals to how much? V naught power? It is clear. Similarly, can we find the answer for displacement relation? So we can start to the same. A equals to, and the A is minus kV. So A we can write as V dV by dx.
Yes.
V gets cancelled. So what we get is dV is minus k dx.
Yes.
When x is 0, we can call the V as V naught. So V minus V naught is minus kx. And because of this relation, we can also say that what is the maximum displacement possible when the rod will come to rest. The maximum displacement of slider.
Sure.
So for maximum displacement of slider bar equals to when V becomes 0, when you come to rest.
Yes.
So the x max turns out to be
In like
V naught by. And if you want to write the answer, it is V naught by V square by. These are some possible questions that you will come across. Okay, not difficult, but just you need to know how to express it. So we have solved how many chapters? You can imagine you have done EMI, current and electricity, magnetism, kinematics.
yes.
So how many chapters you solved?
Sir.
EMI, magnetism, circuit current and yeah, current chapter, then laws of motion, kinematic. 5 chapters.
5. Yes.
One question, 5 chapters. But this is not done. We need to at least add one more chapter.
Yes.
And the next chapter is your work energy power. So we will do the energy and power and energy power, or you can simply energy analysis. So the rod is losing the energy, and that energy which is lost by the rod is actually appearing as the energy through, or getting, it is getting dissipated through the resistor of the circuit. Because in a circuit we don't have any energy storing element like capacitor or inductor. What we have is pure resistor, so it will definitely dissipate the energy. So you may be asked that how much energy is lost by the rod, or you can say how much energy is dissipated through the
Yes. Yes.
resistor.
Yes.
Because we know the velocity as a function of time t. This is really interesting because if you remember, the I induced was BLV by R, and we can clearly see the V itself is V naught e power minus kt. So in a way, the I induced is, and this is the current at t equals to 0. So this is I equals to, I can say. So when you start moving, the potential was BLV naught. So the current was BLV naught by R. So this is a very exponentially decaying current, right?
Yes.
So there are two ways in which we can solve this question. The one is the amount of heat dissipation by the Joule's law of heating. We can write I square R dt. And because we know I as a function of time t, so this is pretty much straightforward calculation.
Yes.
So uh, we can write I naught e minus kt whole square R dt, and then you can do it from 0 to t, or you can get for any time interval. So this is basically I naught square R and the power becomes double, so 2kt. And the moment you just express, you will get the answer as I naught square by r upon 2k 1 minus, and the k you can replace. That's totally okay. I naught is how much? It is so delta H becomes this much, and I naught we can write as v square L square. Okay, so what I'll tell you, okay, this entire term, will actually become, I will, if you do the calculation, you will get the answer half m v naught square. Yes. And that is logical because we know that it is the loss in kinetic energy of the rod which is actually dissipating as heat energy.
Yes, sir.
So alternatively, this you can say cumbersome calculation is not required. Once you know the velocity, you can directly say that the delta H is delta K loss, and that's why it is half m v naught square minus half m v square, because we know the loss is, and because v is v naught e power minus kt, so you can clearly see the answer in one line. This is alternative method, alt. We got the line answer in one line, right?
Yes, sir.
So they may ask you the heat dissipation as a function of time t. So what is the maximum heat that we can dissipate? The maximum energy that we can dissipate is the initial kinetic energy of the rod.
Yes, sir.
Can we dissipate more than this? No. We don't have energy more than this, isn't it?
Yes, sir.
Okay. They do ask question of power, the instantaneous power. So because the rod is slowing down, so power of the power, you can say here as F dot V relation. And if we write for rod, and F is on the left, it was ILB, and velocity is right, so we can say ILB. And the instantaneous power we can write as minus because it's losing the energy. I itself is BL V by R. And then we still have BLV again. So the power is actually B square L square V square by R. Or the best way to remember is it is BLV by R whole square into R. And what is BLV? It's a EMF induced, right?
Yes.
And this is like a current, the instantaneous current, right? Why I'm writing like this is just like minus E square by R. So BLV is the E, right? So the instantaneous power is equivalent of minus E square bar. So power through the resistor is plus E square bar. Okay. Because the net power of system is zero, because whatever energy, whatever the rod is losing the energy is the energy gained by the resistor. So if I take the system together, the sum of the power must be so that's logical, right?
Yes, sir.
So we have done all sort of analysis. So they may ask you find the power or find the heat dissipation when it travels half of the maximum. So rod will travel up to some maximum which we have determined, and it was linear equation. So at a halfway, your velocity will also become half, isn't it?
Yes.
If something is linearly decreasing, so I know initial is V naught and final is zero, and it's linear equation. So exactly at halfway distance, the velocity will also become half. Do you agree?
Yes. Yes, sir.
And therefore, the till you travel half of the maximum, how much heat will dissipate? The answer is half m V naught square minus half m V naught by 2 whole square. Is this clear?
Yes, sir.
So these are the all the variety of question that you can expect in this chapter. And this was the first scenario. So let's try to go back and think more about the problem that we just solved. So this is the simple R circuit, and how we started with. So first we used the idea of motional EMF, and very much we got the answer also for that. And after getting the motional EMF, we got two things which a circuit can give you possibly: current. So in this case, we have just current, and once we got current, then we were looking for a velocity of the rod. So we thought about the acceleration, and so we thought about the laws of motion, and therefore we have to do the ABD, which we did, and we got the acceleration. And once we have the acceleration, we knew the kinematical relation that how to proceed further, and so we got the other part as well. And then we back substituted the value of V in all equations to get the T relation, and eventually we got the heat dissipation and all. But let's think of the entire circuit as a energy concept. Energy concept. So as per the energy concept, this entire circuit is actually following the conservation of energy, and the kind of conversion that is happening here is conversion of mechanical energy into electrical energy, right? So so whatever heat is consumed by the resistor, heat dissipated by the resistor, the energy consumed by the resistor is at the expense of energy lost by the rod, right?
Yes, sir.
So it is logical that the rod must slow down. That's very much logical. So at the end of the day, nothing can be driven without energy. So EMI is not the exception. Okay. It has to follow the I mean conservation of energy in a way which is not very intuitive. I mean, of course, we are not very much habitual of looking at it in this fashion. It is always there. Okay.
Yes, sir.
The next part is, what if in the same R circuit, what if we have a constant agent which is constantly supplying the energy. So we are trying to create a circuit in which the agent is at constantly working towards the energy supply. So we have resistors. And now earlier we gave a certain amount of energy to the rod, which is half v naught square, and the circuit was driven till it was in motion. But now we are going to not give you energy, rather a source of energy. So it is like the kid is going along with the father to a mall. The kid is not supposed to worry about the money, the energy part. You just raise your interest, and it will be fulfilled if it is a legal one. And the money will keep on coming from the source that you carry.
Yes.
Here's the situation. If we apply a force on a rod to the previous circuit, the energy is not an issue. I will keep on getting it, right?
Yes.
And if I keep on getting energy, what will happen? I mean, if let's say if the rod is getting energy at some rate, the rate is, let's say, uh, maybe 100 joule per second, then it will dissipate. Some of the energy will be dissipated by the resistor. Let's say the resistor is dissipating at 60 joule per second. Then the rest of the 40 joule will actually increase the speed of the rod. Understood?
Yes.
But as you increase the speed of the rod, it will be able to create a bigger EMF. A
Yes.
bigger EMF means bigger current actually, and bigger current means the resistor will dissipate more and more, isn't it?
Yes.
So at one go you get more energy, at other go the resistor starts dissipating more and more. So a time will come when the rate at which you consume receive the energy from the agent, the visible agent, in this case the source, and let's say at the same rate the resistor start dissipating the energy. In that scenario, the rod will get nothing, isn't it? The rod will get
Yes.
nothing. And if the rod will get nothing, it means whatever velocity the rod has attained till that instant, that velocity of the rod will be maintained. It is clear?
Yes.
And that is maintained is equivalent of saying that the rod will attain the terminal velocity. So the word terminal means it will terminate at that value. So velocity will terminate. So we call it terminal velocity. So the end goal is to find the terminal velocity, but the first goal is how to proceed this question. So at t0, we believe that v is 0. So we start from rest. So at the very beginning, we don't have any EMF. Okay. But at a later instant, so at a later instant, what will happen? Tell me. The rod will have some velocity, isn't it? So at t equals to t, we have v equals to v. So sorry, yeah. So now what we can see that we are in a position to start analyzing the situation. So at this instant, we have some velocity. The force is still intact. So what is the process of solving questions like this? How we proceed? The first step is you start from EMI.
Yes.
Okay, fine. So go ahead.
Okay. So so we are supposed to figure out what the terminal velocity is.
Yeah, that's the end goal, of course.
Okay.
So in the process, you have to first find what is the velocity as a time function, maybe. Okay. So
Yes.
first you figure it out like what is the I induced and E induced. You start with I and E, right?
Yes.
Then next step is you write the ability to get a how v is changing relation.
Huh?
Yes, tell me. What the answer? Just tell me.
Sir, I'm getting EMF induced. Yes, sir.
Okay. We got the EMF induced, right?
Yes, sir.
So the E induced is always BLV without any doubt.
Yes, sir.
So I induced is always BL by R for this circuit.
Yes, sir.
And now comes the, this is okay. I'll make a boxes. Okay, that's really nice to make a box and understand. We have done with the one step. So what step we are done with is the current EMI chapter. So we are done with EMI chapter.
Yes.
After EMI chapter, we'll go to magnetism. Magnetism. So the next goal is magnetism.
For it's due to the magnetic field momentarily, yes, IL.
That's it.
Yes, sir.
If magnetic is ILB, we are done. Then
Yes.
third is the laws of motion, right? So we'll first write the draw the ABD. So now ABD, free body diagram of the rod, and then one is the applied and other is the magnetic force. And this is going this way. So net force equals to mass into acceleration, we can write F minus ILB equals to M into A. Correct?
Yes, sir.
So we're done with which part?
Sir, so
Laws of motion.
yes, sir.
And once you have the laws of motion, what I'll say is substitute the value of I and all. But something
Yes.
really interesting. Since we were looking for terminal velocity, so for terminal velocity, the rule is simple. You first come to this extent, I mean, come to the laws of motion part. And the moment the rod will attain the constant velocity, its acceleration will vanish. Isn't it?
Yes, sir.
So just substitute A0 in the third equation, I mean, third box. So box 1, box 2, box 3. So box 3. Now if you substitute A0, what you get? F equals and now you
B
can write
square L
as,
square.
yeah, I is BLV. So it is B square L square by V by R. Correct? This one.
Yes,
And
sir.
this is the V terminal. So V terminal velocity we write as FR by.
That's it.
This is what you can expect up to JEE level. No, but we can go much beyond this. So we can go for the velocity as a time function because we have laws of motion. So we have the A, and because we have A, we can use the laws of motion kinematical equation.
Sir, I found that one, sir.
Pardon?
Sir, I found that one.
Very good. So this was B square by V is MA. So A turns out to be how much? A by A
F
minus
by B square by
V
L
square.
square by M R.
Correct?
Yes, sir.
So for the preciseness, we can write this as alpha minus beta V,
Yes, sir.
where alpha is F by M, beta is B square L square by M. And if you make such a adjustment, then it is easy to write the. So now, so this is the box we got, and then we go to kinematics box.
So, but for integrating, we have to take the common, I mean, like we have to make such that it has,
So
or it's not completed.
it is quite integrable.
Yes, sir.
So we have the kinematics block. So I'll go to next page. So because it's a is a v function, so we can write dv by dt. This is the differential equation. Now, if a v is differentiated with time, we get this number. So what number will give you? Let's see what kind of thing will give you this number. Okay.
So,
No, don't worry. So now we can solve the differential equation. dv upon alpha minus beta v equals to dt, right?
yes, sir.
When t was 0, there was no velocity. So it was also 0. So this will give you ln alpha minus beta v upon minus beta 0 to v equals to t. So if you put the limit, it is alpha minus beta v upon alpha is minus beta t. So alpha minus beta v by alpha is e power minus beta t. Okay. Understood?
Yes, sir.
Okay. And actually, this is like a drag force. This is the constant force. So alpha is trying to give you the acceleration, but beta v is trying to drag it. So it is trying to slow down. And definitely when a will be 0, beta will be v will be alpha by beta. That's called the terminal velocity. So if you rearrange, you will get v equals to alpha by beta, which is expected 1 minus. Okay. So that's very easy to remember. The moment we have a formula a equals to alpha minus beta v, the answer is simple. The drag will it will decay you exponentially. That's the whole idea.
Yes, sir.
So it will create a decay of this value, and alpha will try to increase constantly, and then you can always write like this to get the answer like this. So decay factor is called drag force. Drag force is something which you write as minus bv, we call drag force equivalent, and b is called the drag coefficient in a context. So this
Yes.
is v equals to alpha by beta, and definitely if t tends to infinity, so technically that's called the steady state scenario. The steady state so in the steady state, the v becomes alpha by beta. That's it, right? Because e power minus infinity is 0. So this is called the terminal. So if you want to get the answer through the mathematical rigor, you can do it up to here, then make t tends to infinity to get the terminal velocity. Otherwise, we can get it from directly from here, right? By putting a equals to 0.
Yes.
Probably we can also do it for the x, but it is going to be very complex. So let me do it. Let's see how complex is that. So for v versus x relation, we can say v dv by dx is alpha minus beta v. This is v dv by and to solve this we have to do a lot of manipulations which I can do. So I can write as alpha minus beta v minus alpha so I can write as alpha minus alpha minus beta v dv, I'll write later on, upon beta into alpha. See, is it same question, right? Do you realize
Yes.
the LHS is same question? Because the numerator is still beta v, and beta below will cancel out, so it's v dv by this. But now we can separate the term two terms. We can write as alpha dv by beta alpha minus beta v minus dv by beta, right? Because
Yes.
so we have alpha by beta, we can take common, and this is the answer which we got. So dv by this will be how much? Yeah. So this is ln alpha minus beta v by uh, alpha by minus beta. Yeah.
Yes.
Minus v by beta. So minus alpha by beta square ln alpha minus beta v by alpha. So definitely we cannot solve, right? So we can write as beta x equals to alpha by beta square ln alpha by alpha minus beta v. So at least we are going to get the implicit relation like this. Okay. So that is what we have to stop. I mean, of course, you cannot solve it by any mathematical manipulation. There is something called numerical analysis, by which we get some close approximate value by converting the formula into uh, what we call expansion formula of logarithm. So we can keep some of the term, and then yeah, that's it. So no need to worry. I mean, they will not ask you a question which is difficult. They will ask a question which is doable only. This is the relation.
Okay.
And further, we can add the energy analysis. So the energy analysis is obvious. So for rod, it is F minus ILB into V, the instantaneous power, and so on.
Yes.
So I'll stop it here. That's a logical way to stop. And you can start solving EROW, IE EROW. Okay. Or better, you can start solving SCORA first. So solve SCORA, finish as much as possible. We'll do some more practice, then you can solve all entire EROW with ease. That's not difficult.
Yes.
Okay.
Okay.
So bye and take care. See you in the next lecture.
Bye, sir. Thank you so much.